In this video, we will discuss the paper complementing model learning with mutation-based fuzzing, that we can combine a mutation-based fuzzer with a generic evolutionary algorithm to find more counterexamples during model learning. The framework LearnLib is used to provide the various implementations of the algorithms. As testing algorithm, we use a customized WP algorithm, and as learning algorithm, we use TTT. The fuzzer used is American Fuzzylab. It is slightly altered to save output data because the implementation of the learning algorithm needs this information. The customized WP normally uses randomly generated inputs until it finds a counterexample. This, however, is not always effective. By using AFL to find inputs that cover a big part of the code, we can instead use these set inputs that have a guaranteed high coverage of the code. This causes us to have a higher probability of finding an error, because we don't use a random input that might barely cover anything. Because of this, the average time required to find errors should be shortened, and there should be an increased chance of actually finding an error in the first place. For the user, this error is preferable because it can find more errors in a shorter time. The downside, however, is that AFL takes a long time to find the correct inputs. AFL is a mutation-based algorithm that makes slight changes to the input to find inputs that have a high code coverage. In the original paper, the 2016 RES challenge was used to quantify the various results of the various implementations. In our experiments, we have used the latest RES challenge of 2019 to evaluate the various systems once again, but with different problems. At the moment of recording, the RES challenge has just ended, and only yesterday the results have been published. We used the code provided in the Git of the original authors to run the active learning program. First, we compile the American Fuzzylab implementation to make a library file. This library has to be added to the common libraries. These instructions can also be found in the README of the Git. After that, we build the active learner, and then we can use our own provided scripts to run these systems. These scripts can be found in our GitHub repository. We've created this repository to store the various scripts and bash files we've created to make it easier to run the processes on the RES challenges. In the repository, various README files can be found that explain how to use these scripts and bashes for the various tasks. Basic learning and fuzzing, it's necessary to prepare the code, because the processes cannot be run simply on the source code. For fuzzing, this means you have to run fuzzingproblems.py. This prepares the code for fuzzing. Then you can use a bash file to compile all the problems, and then you can simply run them with our custom bash file too. It only asks for a problem number and a timeout. It's also possible to run all these problems in a batch. Because this fuzzing is limited by the amount of cores we have, it only runs a maximum of 7 processes. So you will need to do this multiple times. For basic learning, we also need to prepare the code. This time we use learningproblems.py. After that, we still need to compile all the problems. We've created a bash file to make this simple, and this bash file compiles all the problems using G++. The default settings are used. Luckily, the basic learning can be run in parallel, unlike the fuzzing. So, to execute all the problems, we have made a bash file named execute_all. This executes all the problems, as you can see in the experiment. On screen, you can see how we will execute all the basic learning tasks. We simply use the execute_all bash, and then we enter a timeout. In this case, we use 4 hours. As in the experiment. Now you see various terminals open that start all the processes in parallel. You can see that they all start the process simultaneously. Similar to basic learning, the fuzzing is also run through the bash script. provided in our kit. After preparing the code, you can simply run this command as seen on screen, and it will start the processes. Different to the basic learning is that this fuzzing is limited to the amount of cores and is not running all tasks in parallel, but will only run as many tasks as there are cores. In our experiment, we have also run the combined learning and fuzzing using a bash script. This bash script uses a timeout to limit the time used for learning, but you also have to input which problems you want to process. Beware that in this case you should manually make sure that you do not add more problems than you have cores. You should also state whether you want to do the fuzzing or not. Because fuzzing also had to be done separately, this has already been done in our experiment, and thus we use the previous results. It will again start the tasks in parallel. In our experiment, we had to run our programs for only a short while. This has been done because of the time limitations of the project. Regretfully, this means we do not have the an exact similar result to the paper, which ran some programs for up to 10 days. We do, however, see a similar trend where the combined learner learns a lot more states and a lot more paths in a shorter or same time. We simply ran the fuzzer for 4 hours and gave the basic learner and combined learner 4 hours to run too. The combined learner, though, was often done in 10 minutes and already had a model. A clear shortcoming of this program still is that we need to run the fuzzer first and then the combined learner instead of just the basic learner. But the gains in the found state and paths seem very much worth it. One such example is the problem 14, where the basic learner found 183 states, but the combined learner found 672 states. This difference is quite large, especially for a program that has only been run for such a short while. In the case of errors, we see that the combined learner is often the same, slightly lower or higher than the other methods. We conclude that this is mostly because we run programs for a very short while and it was simply unable to find more errors in that time. We are not sure what the result would be if we had run this process for far longer as done in the paper. We expect it would mean that the combined learner found more errors because it's far more effective as seen in the states and paths. Because recently the RARS challenge has concluded and the results were published, we took a peek at it to see how well people were doing with various programs. We noticed that there were not a lot of contenders, and we feel that if we had run this program for a longer while, and maybe on a dedicated server, that we could have contended in this challenge and maybe actually won prizes. We regret that we haven't done this, but we do see that this program would be very effective. In conclusion, when we compare our results to the results of paper, we see that